In this lecture, we will discuss the expression for the current waveforms for the half bridge inverter circuit. So we have already discussed the operation of the half bridge inverter circuit in one of our previous video. So the waveforms for the half bridge inverters are shown in front of you. The voltage is plus Vs by 2 for the half cycle and minus Vs by 2 for the rest of the half cycle. And for the inductive load, the current varies like this, that we have already discussed in the previous videos. So you can refer to those videos to get a detailed explanation of this one. So our current starts from some minimum value I1 and reaches to the I2. During this portion, when the current is positive, your main switch will be turned on, and during this portion your diode will be turned on, and then your main switch will be turned on again. So the diode in the half bridge circuit helps to provide path for the dissipation of the energy that is stored in the inductor. So now let's analyze this waveform by dividing into two intervals. The first interval is the first half cycle, so that is from 0 to Ts by 2, that is the first interval. And in this interval, if we write down the equation for the circuit, the source voltage must be equal to the load voltage, and in the load we have two components, the resistance and the inductance, simple RL circuit. So the voltage across your inductor is L di by dt. The voltage across the resistance is Ri, that must be equal to Vs by 2. So if we solve this equation, the solution of this first order differential equation is given by this expression, that I of t is equal to a into e raised power minus RL t minus R by R into t plus Vs by 2 into R. Okay, so let's define a time constant for this inductive load, that is equal to that tau is equal to L by R. So using this value of the tau, this equation can now be written as a into e raised power minus t by tau plus Vs by 2R. So let's call it equation 1. Now we need to evaluate the value of this constant a, and that can be determined by looking at the boundaries of our selected interval. So at time t is equal to 0, at this point the current is I1. So if I take this boundary, so if I say at time t is equal to 0, if I look at the current I t naught or I of 0, so that is equal to I1, right? So using this value of the I1 for this current IT, and at time t is equal to time equal to 0, so from this equation 1, if I come over here, so I1 will be equal to a into e raised power 0 plus Vs by 2R, and from here we can find out the value of a. So as a is determined, now we can place it back in our equation 1, that is this equation. So from this equation we will get this equation, I of t will be equal to I1 minus Vs by 2R into e raised power minus t by tau plus Vs by 2R. So let's call this equation as equation A. So this is the solution for the load current for the first interval, that is from 0 to Ts by 2. So if we place the value of time over here, and we know the initial current I1, so we can determine the current at any instant of time in this interval starting from 0 to Ts by 2. Okay, so the ending current of this interval is I2, that is the maximum current over here. So that can be determined by taking the time equal to Ts by 2 in this equation A. So in this equation A, if we take t is equal to Ts by 2, so the current at that time Ts by 2 is equal to I2, capital I2. So now if we apply these condition over this equation A, So this I of t is equal to I2, and this time t is equal to ts by 2. So just replacing these values in the equation A, so we get the value of I2, which is defined by which is being given by this equation B, right? So this is the value of the maximum current that is at the end of the interval when the time is equal to ts by 2. Okay, now let's discuss about the second interval. The second interval is this one that starts from here when time is equal to ts by 2 and goes up to time ts. So total length of that one is same as that of your previous selection, that is equal to ts by 2. So if we write down the equation for this one, for that inductor voltage plus the voltage across the resistance must be equal to your supply voltage. So supply voltage in this second part is minus Vs by 2. So the equation for this second interval starting from Ts by 2 to Ts is this L di by dt plus Ri, that is equal to minus Vs by 2. So if we look at the solution of this equation, this is I of t, that will be equal to b into e raised power minus r by l into t minus Vs by 2r, and taking tau is equal to L by R, so we can write down this equation in terms of tau. So B is equal to e raised power minus t by tau minus Vs by 2R. So basically this equation is for the time starting from Ts by 2 to Ts. So this equation now can be written like that: I of t that is equal to b into e raised power minus Ts by 2, t minus Ts by 2, not t is over here. This is we are updating it, t minus Ts by 2 by tau minus Vs by 2r. Now this equation will be valid from Ts by 2 to Ts. So when t will be equal to Ts by 2, so that will be the starting in point of your second interval, that will be considered as 0 over here for the second interval, but actually it is Ts by 2. Okay, so the solution for the current for the second interval from Ts by 2 to Ts is this one. So in this equation we need to determine this B. So for B we can apply the boundary condition that at time t is equal to Ts by 2, our current is equal to I2. So taking this current in this equation 2, right? So if I take I of t is equal to I2 and then t is equal to Ts by 2, so this will become 0, so e raised power 0 will become 1, so it is simply B, then minus Vs by 2r. So the value of B will be this one, I2 plus Vs by 2r. Now if we use this value of the B and place it in equation 2, that is this equation, so the solution for the second part can be written like that. This is I of t, right, in the second interval. This is not I2. So this is I of t, that is equal to I2 plus Vs by 2r, that is the value of B from here that we are placing in this equation, into e raised power minus t minus Ts by 2 by tau minus Vs by 2r. So this is the equation representing the solution of the current in this second interval. So you must consider it I of t like that. Okay, now if I go and look at the waveforms, so the I1 and I2 must be equal in magnitude because the area covered above the time axis and below the time axis must be same, so that there is no DC component in the output of the inverter waveform. So I1 and I2 will be equal in magnitude but will be opposite in sign. So if I1 is negative, then I2 is positive. So I2 can be written as equal to minus I1. So if we look at this equation B that we have determined from the analysis of the first part, that is from 0 to Ts by 2 interval, So in this, if I replace this I1 with minus I2, because they will be equal in magnitude but will be with the negative sign. So taking this equation B, and that is equation this one, I2 I is equal to I1 minus Vs by 2r e raised to power minus Ds by 2 by tau plus Vs by 2r. So in this equation, looking at the waveform symmetry, we are replacing this I1 with I2. So now if we rearrange this one and bring I2 terms on the left hand side, so I2 into 1 plus e raised to power minus Ts by 2 tau, right, and that will be equal to Vs by 2r, and this term is common between this term and this term, so Vs by 2r into 1 minus e raised to power minus Ts by 2 tau. So from here, if we simplify for the I2, so the expression for I2 is this one, and I1 will be equal in magnitude but will be with the opposite sign, so I1 will be this one. So we can determine the maximum current and the minimum current in the half bridge inverter with the help of this analysis, and we can determine the current at any other instant of time by writing down the equations for the current, and for the first half cycle the current solution is this one, and for the second half cycle the solution of the current is basically this equation. In this I2 should be considered as I of t. Okay, so now let's look at the example. So this example says the source voltage of a single phase half bridge inverter is 200 volt. The load consists of 10 ohm and the 25 millihenry inductance, and the output frequency is 50 Hz. Determine the following. First of all, instantaneous output current at the end of the first cycle. Secondly, steady state current expression for both half cycles, and third is the THD in the load voltage and the current. So we have already discussed the THD expression in our last video. For detail you must refer to that video. Okay, so now as it is the half bridge inverter circuit, so our output voltage will be varying between minus 100 and the 100 volt when we have applied 200 volt supply. Okay, so voltage is equal to Vs by 2, that is 200 by 200 volt, and the time constant for this particular example, that will be equal to L by R, so 25 millihenry divided by 10 ohm. So time constant is this one, and the inverse of time constant that can the switching time Ts that will be equal to 1 by F, so that is equal to 0.02 second or 20 millisecond. Okay, then we can look at Ts by 2 tau, that will be equal to, if we plug in the values, equal to 4. And basically we are calculating these parameters for this equation, because in this you can see we need these part Ts by 2 tau. So Ts by 2 tau is required over here, Ts by 2 tau is required over here. So Ts by 2 tau is equal to 4. Now if we take this expression for the maximum current, that is I2, so this expression is this one, so we just need to plug in the values. So our current comes out to be 9.64 ampere, the maximum value, and the I1 will be of the same magnitude but with the opposite sign, so I1 will be minus 9.64, right? So now for the expression of the current for the first half cycle, I of t that is equal to I1 minus Vs by 2r into e raised power minus t by tau plus Vs by 2r. So we just need to plug in the value. I1 we have already calculated, that is minus 9.64. Vs is known because in the derivation we considered Vs as the supply voltage and Vs by 2 is the voltage that is appearing, so this will be 200. So 200 by 2 into r into e raised power minus t by tau. The value of tau is over here, 0.0025. So then plus Vs by 2r. So plugging in the values, so we get this expression for the current. So this is the current which this is the expression through which we can calculate the current at any instant of time in the first half cycle of your current. So you need to place the values of the t, and you will be getting the values of current over there. Now for the second half cycle, as we have already seen the expression, this equation C gives us the solution for the second half cycle. So using this equation over here, I of t is equal to I2 plus Vs by 2R into e raised to power minus Ts by 2 by tau minus Vs by 2R. So just plug in the values. So the expression for the second half is this one, right? So if you look at this equation A and B, the equation A is the solution for the first half interval and equation B is the solution for the second half interval. So both are exactly same with the opposite signs. Over here we have 10, over here we have minus 10, minus 19.64 plus 19.64, and e raised to power minus 400 into t. So for the second half in part, as our frequency is 50 Hertz and the half time period is 0.01, so you can say it is appearing over here, right? So from this part, the time is delayed by this one, t minus 0.01, the time of your half cycle. Okay, so we have determined the expression. Next thing that was to be determined is to look at the steady state current expressions for both half cycle that we have seen, and now we want to look at the THD in the load voltage and the current waveform. Okay, so and to calculate the THD of the current, we need to look at the components of the harmonic components of the current, and those depends upon the impedance of your circuit. The impedance of inductive load is the function of the frequency, because we know that the impedance is magnitude of the impedance is R square plus n omega L square, inductive reactance basically. So reactance varies with the variation of the frequency, because reactance is equal to omega L, and omega is equal to 2 pi f. So reactance is equal to 2 pi f L. So when the frequency will change, the impedance will change. So we are going to take n over here, n into omega L. We are multiplying this reactance omega L with the n, where n is the effect of the frequency. If your frequency is, let's suppose fundamental frequency is 50 Hertz, and the second harmonic frequency will be 100 Hertz, third harmonic frequency will be 150 Hertz. So n will be modifying that frequency and modifying this reactance. Okay, so impedance for different frequencies will be different. Okay, so let's calculate the different magnitudes of the impedances for different frequencies. So for fundamental component, let's calculate. So Z1 is equal to under root of 10 square, where R is equal to 10 given in the question, and then n is equal to 1, because we are calculating it for the fundamental. Omega is 2 pi f into L, the square of that, and then the under root. So just plug in the values, value of the inductance and the frequency, and evaluate it. So impedance offered to the fundamental impedance, fundamental component of the current is this one. Okay, now calculating the impedance for the third harmonic. So that will be equal to 10 square plus 3 times the omega L square. N is equal to 3, right? So if we look at the omega L, so omega L can be calculated as 2 pi f into L. So that comes out to be 7.854. So if we take this 7.854 into 3, so this is the impedance offered to the third harmonic. Similarly, we can calculate the impedance for the fifth harmonic by taking n is equal to 5 over here. So then impedance for the seventh harmonic, so same expression, but n is equal to 7, so 7 into 7.854, the square of that one, and then evaluating this one, this comes out to be 55.88. Then the impedance for the ninth harmonic. So let's summarize this information in this table, that for the fundamental component, the impedance is this one. For third harmonic, this is the impedance. For fifth harmonic, the impedance is this one. For seventh harmonic, and for the ninth harmonic. And if we look at the voltages. So the voltage will be now we will have to look at the fundamental component of the voltage, and the fundamental component of the current will be determined by dividing the voltage of that particular harmonic with the impedance of that harmonic. So we need to calculate these fundamental components, the harmonic components of the voltage. Okay, so the voltage waveform is the square waveform that you can see over here, and for the square waveform, the expression for the if you represent that one in with the help of the Fourier series, so the voltage will be equal to Vs by 2 divided by n pi into sine of n omega t. So basically that will be given by this expression. This is the expression, Fourier representation of the square waveform. So 4v by n pi into sine of n omega t. So in the half bridge inverter, so the square waveform is varying between minus Vs by 2 to plus Vs by 2. So its Fourier series representation is this one. So basically we are using this expression, right, summation of all harmonics. So in this we will be changing the value of the n, that is the harmonic component, harmonic order. So we are calculating the magnitude of the voltages for different harmonics. So this is the peak of the voltage. So divided by under root 2 we will get the RMS value of the harmonic voltage. Okay, so if we divide it by under root 2, that will be equal to under root 2 Vs by n pi. So RMS value, if I move to this table now, so RMS value of under root 2 Vs by pi. So Vs is given to us if we plug in the values. So V1, V3, V5, V7 and V9 can be calculated, and then we can calculate the current by dividing this voltage with the corresponding impedance for the first harmonic. So third harmonic voltage and impedance for the third harmonic, fifth harmonic voltage, impedance for the fifth harmonic, and so on. If we use those one, we can find out these currents. And the expression for the current THD, that the harmonic current compared with the fundamental current. So harmonic current is the summation of the third harmonic, fifth harmonic, seventh harmonic, ninth harmonic. We have calculated up to ninth harmonic. So square waveform has only the odd harmonics in it. There are no even harmonics. So we have calculated the odd harmonics. So I3, taking from this table, I3 is there, I5, I7 and I9. If you pick up those values and you solve it, so this comes out to be 18.11%. And if we look at the voltage, so the voltage can be calculated in the same way. The THD in the voltage waveform, that can be calculated by taking the square of this third harmonic plus the square of fifth harmonic plus the square of the seventh harmonic plus the square of the ninth harmonic, and then taking the under root and dividing it by the fundamental component. You can find out the THD in the voltage waveform. The other way around is that you calculate the total voltage, and from that you subtract the fundamental component. So rest of the voltage will be the contribution of all the harmonics, right? So as the waveform of this half bridge inverter is the square waveform, so the peak value is basically the RMS value in the case of square waveform. So as we are applying the 200 volt, but our output voltage will be between minus 100 and plus 100. So the RMS value of this square waveform will be equal to the peak value, that is the 100 volt, right? So 100 volt is the total voltage at the output, and in that the fundamental component is this one, 90.03 volt. So from applying this one, the total voltage 100 square minus the fundamental square, that is 90.03. So divided by the square of the fundamental component, that is 90.03 square, and then taking the under root. Okay, the complete under root, it's the under root of the whole of this expression. So this comes out to be 0.4835. So the THD in the voltage waveform will be 48.35% for this square wave. Now let's look at the second example. A single phase full bridge inverter feeds a resistive load of 5 ohm. The source voltage is 100 volt. Determine the RMS value of the fundamental component of the output voltage, output power, harmonic factor for fifth harmonic, distortion factor for fifth harmonic, THD, LOH and corresponding HF. So single phase full bridge inverter is there. So in the case of full bridge inverter, your output voltage waveform is between what it varies between the supply voltage level. So from minus 100 volt to plus 100 volt. So the Fourier series expression for this square waveform is given by this one, that is equal to 4 Vs by n pi into sine of n omega t. So the peak value of any harmonic voltage is this one, 4 Vs by n pi, and the RMS value will be 4 Vs by under root 2 n pi, that is 2 under root 2 Vs by n pi. So the first part is to calculate the RMS value of the fundamental component of the output voltage. So by replacing n is equal to 1, we can find out that one. So that is 90.03 volt in this waveform, and the power that can be determined by taking the square of that RMS value of the voltage divided by the resistance. So resistance is given to as 5 ohm, and the RMS voltage is total RMS voltage is 100. So 100 square by 5, so 2 kilowatt is the power that is being dissipated across the resistance of this particular inverter. So across the load of this particular inverter. Okay, then calculating the harmonic factor for the fifth harmonic will be because in the question it was harmonic factor of the for fifth harmonic. So we need to know the RMS value of the fifth harmonic and the RMS value of the fundamental component. So for fifth harmonic, if we refer to this expression, so by replacing n is equal to 5, we can find out the RMS value of the fifth harmonic voltage. So that is 25.4647, and the this is basically the peak voltage for the fifth harmonic, and for the fundamental harmonic it is 127.32. So either you can take both of these one as the peak values, or both of these ones can be the RMS one. So the harmonic factor comes out to be 0.2, that is indicating that the contribution of the fifth harmonic is 20% with respect to your fundamental component. Next is to evaluate the distortion factor for the fifth harmonic, that is the harmonic content when your waveform is subjected to the second order attenuation. So the expression, as we discussed in the last video, for the distortion factor is that the RMS value of that harmonic voltage or current divided by the square of the harmonic order and the fundamental component. So if we plug in the values, this is equal to 0.008 distortion factor of the fifth harmonic. And now if we calculate the total harmonic distortion is Vrms square minus V1 square by V1 RMS. So if we just plug in the values, that comes out to be 0.4835, so that is 48.35. So the THD for the square waveform is fixed, that is always 48.35%. Okay, so now let's calculate the voltages for different peak voltages for different harmonic. For third harmonic, the peak voltage will be 42.44. The fundamental is 127.32. For fifth harmonic, it will be given by this expression, right? So if we look at the 3% of our fundamental का 3% से जो the closest harmonic to the fundamental, so that is of more than 3% magnitude of the fundamental, that is the lowest order harmonic. So that is the third harmonic in this case. 44.44 is more than the 3% of your fundamental. So third harmonic is the LOH, and RMS value of this one is 30.01 volt. So harmonic factor for the third harmonic is V3 by V1. So that comes out to be 1 by 3. That means the third harmonic is 33% of your fundamental component. Okay, so now let's conclude this lecture. So what we have learned in that one, we have seen the expression for the current in the half bridge inverter. Okay, so that was this one, and for the first half cycle the solution is this one, and for the second half cycle the solution is given by this equation, and we have seen the expression for the maximum and minimum current in the case of inductive load, and then we have seen two examples in which we have calculated we have developed the expression for the currents, and we have seen some quality parameters for the inverter waveforms. We have determined the THD in the current waveform, we have determined the THD in the voltage waveform, and we have seen that how we can calculate the different other performance parameters. So that's all for this video. Thank you. In the next lecture we will discuss the current expression for the full bridge inverter, and we will see some examples for some more examples for the evaluation of the performance parameters.